Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 74. In today's lesson, we are going to be looking at hash tables. So, a hash table is a structure that we've used before, but we haven't discussed it as such. So, the dictionary in C Sharp uses a hash table. So, we'll look at what that actually is. So as we get started, so the purpose of a hash table is it gives us another tool to use to work with data, another data structure. So it benefits from its search time is big O of 1, so constant time on average. In worst case, it's a linked list, so in that case you get linear time, but in average case, it's a or constant. In best case, it's also constant. That's nice because because we're doing something called hashing. So instead of searching for everything, we're doing a hash and then searching through the table. So a hash table is something that stores data into a pre-computed location. So you'll do the computation to figure out where to store it at, and then when you go find it again, you'll just search that location. We're going to see one way to do it today, but there's other examples you can do and other things you can do, but we're just going to look at the basics today. So what you can do, you calculate where the item should go, and you go directly there. So the usual concept you'll hear with this is you're taking things and storing them into buckets. So maybe you have something like this. You do a comment. So you might have a couple buckets: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here, if we get say we get, say we're storing numbers, and we're going to do it based on the mod. So this would be mod 10. So it would be whatever's in the ones digit makes the determination. That's what we're going to implement today. So say we've got the number 123. If we were storing it, we would do 123 mod 10, which gives us a remainder of 3. That tells us to store it in bucket number 3, which happens to be 2. So we would get 123 here. So the indexes are going to be off by 1 as we were used to with arrays. So one thing to keep in mind. If we got another number, let's say we get 97. So 97 mod 10 will return you a 7, which puts you in this bucket. So that's sort of what we're going to do. And if we get another number, say we get 17, it gets the same thing, and there it goes. See, that's starting to look like you have a bucket number 6, which is the 7th bucket. And if you kept going, you could get a linked list. And in that case, it's looking like linear. You would have to search through linearly. There's other things you could do from this point to make it a little quicker, but in average case, it's generally, if you're going to use it, it's probably not going to get there. So in C Sharp, the way you do it's something called a hash code. We're not going to actually use it today. There's a built-in one for this. So if we have a string hello dot get hash code, we may have seen that before here or there, but we haven't used it before. W code. So this will get us some kind of numeric representation of hello. And it gets us that 84669. If we run it again, we should get the same thing because that's one of the things. And we did not. Uh-oh. If we ran it again, what happens? We're getting all kinds of different values. So if that, we're getting different locations. What if it's something that's not a reference? What if code is, I don't know what's a number. I'll do 42. Get hash code. What happens in this case? Does it still change each time? So now we got the number. Seems suspicious. We got the number again. Wonder what's happening there. Let's check one more thing. Let's do a let me get rid of that. Let's do code equals, let's move hello up. So if we change it, let's make it I did it all lowercase, let's just make it 2 upper. This should give us a different string. Do we get a different value? Here we'll need to do that so we can see what the value was first. So we should see different values and they should still be being random. They do. And they do. So that tells you whatever the implementation of get hash code for string is, isn't stable per se. What it's doing is it's using the reference rather than the string. So that's some kind of code that represents that string. And if you run it, here, let's do that again. Let's do it like this. Let's do that. We print it. Then we get code 2 or code 2 equals that. And we won't do a 2 upper this time. Now let's see what happens. We need to print codes. All right, so here we get the same thing. So on each run of this, we're going to, for the same reference, we're going to get the same value. What if it's not a reference? What if it's a value? And there we get the same. So under the hood, it's treating it the same, even if it's a separate call. And I think there's one last one just for my interest. Yeah. So it still knows that it's the same value, so the same memory location. Okay. So that's just a real quick, so get hash code, and when you override the equals method, that's one of the methods you get an opportunity to override with it. So what a hash gives us, you give it the same input and it should give you the same output as it seemed to here. It should be fast to compute, otherwise you're gonna, if it's really, really slow, a good hash is really, really slow. So in that case you would, I guess it's not a good hash. A hash used for cryptography is really, really slow. So it wouldn't be a good to try to speed up an algorithm probably. The other good thing or thing to try with an algorithm is to try to distribute it evenly. So this isn't going to distribute evenly. If we get all 7s from here on out, it's all going to go into bucket 6 and it's not going to be that well distributed. So one question, what happens if you have 2 items land in the same bucket? So that's what's called a collision. That's what happened here. So 97 already was occupying 6 and we got another one. So my strategy here was just to add another one. I believe that's called separate chaining. So it's like each one of these is a separate chain of values. So what I believe in that case is you get yeah, if you do that, you get an average case of insert, search, and delete all being constant time. Worst case, each of them, well, yeah, in worst case, each of them become linear because you could have everything go to the same bucket then you insert and you reach the max size of your internal list, and you have to resize and then you have to move everything. So linear, so O of n. And at that point, it's a just a linked list, and that's why hashing matters. So let's go ahead and implement this. So let me see if there's anything else I wanted to touch on before that. Oh, I mentioned equals and get hash code to sort of work together, and that's why you have to override them together. Good idea is equal objects must have the equal hash code. So there, the two hellos were the same, and when you override your own, you want to keep that in mind. So you don't want something random for hash code. You want it something that each time you compute it, you'll get the same thing. I guess dictionaries, I mentioned them. There's other C# data structures that are built in that do hashing like this as well. There's a hash set. So dictionary lets you put about anything. It's a key value pair. A hash set's a key value pair, but you can only each item you can only have one of, so it doesn't handle duplicates. And I believe there's a hash bag as well, and it's basically a hash set, but you can put more things into it. I'd have to check on that one. I feel like I remember it, but I don't think I've ever used it. Okay. So let me get Rider, and we will walk through an example. I've actually done this example, make sure I could get it to work, and I think I did, so we'll go ahead and just get started. So we'll start with a public class hash table. So this is going to be what we work where we build our hash table. So the functionality here is not going to be that complicated. So we're going to have a read-only list of int array buckets. Now we'll have a constructor. It needs to take in a size. So we'll set the size and create it all initially. So buckets equals a new list of size. Now we'll need to instantiate them. Something like that. And then we'll just say buckets at I equals that. So that gets us our bucket set up. So now we will, let's write a helper first, and I'll go ahead and tell you there's a problem with this helper, but we'll see what it is a little bit later. This could be an expression body member. I'm not going to do it as that because I'm going to show a problem with it. But let's do math.abs absolute value of value, and then we will say mod buckets.length. That'll get us what we're doing here. So I'm going to be doing a table of ints. I'm not trying to make this generic. I'm not trying to make it strings at this point, but I'm just going to do it generically like this. So this will tell us what bucket it should belong to. So let's add our first method. We'll add an insert public void insert int value. So int bucket equals get bucket. So we get the bucket it should go in. Now this is where we would set if it contains a value or not. So if it contains if it already exists, I'm not going to allow duplicates. So I'm going to say if not in buckets at the current bucket, so that's an index contains value. So if it's not already there, then we can add it. else we will skip it. If we were returning a value here, we could say return true, I guess, or return bool, and then this would be return true, return false. I don't think there's a lot of value in that, but you could do that, I guess. Now let's do a contains method. Bool contains int value. So contains, we need the bucket, and all we have to do is what we did here. We just check if it exists. And in fact, if I didn't mind doing the get bucket again, I could probably just copy those and do it like that. I'm going to leave them separate just so we don't have to do the get bucket twice. But I could probably combine these a little more intelligently than what I've set up here. So we'll have a public bool delete int value. So if contains value, I want to do it the other way. If it doesn't contain value, return false. No, return true. We were successful. There just wasn't a value. Else. Now I guess that would be false. Yeah, false. Return false. Else. So now we want to get bucket. So here we are going to do it double. Probably should just use it here. Yeah, we'll just use it here just to make it clear, but there is some duplication going on here. Okay, so we get the bucket. Then all we got to do is this. So we will say buckets at bucket dot remove at bucket. No, wait a minute. Now we'll want to do just a little more. So we will want to say var remove index equals buckets at bucket dot find index of value. Is that all right? What method am I thinking of? It might just be removed. That may be actually all I'm needing. We'll check that. That may be what I'm actually after. All right. So that pretty much gets it. Let's do one more thing. This is so we can display it. So we're going to override the string method to string. I'm going to do a string builder. Probably not 100% required here, but I'm going to do it anyway. There we go. All right. So all we want to do here is we're going to loop through less than buckets.length I++, and then we'll just do some appends here. So sb.append. We'll do bucket. We'll use the number there. sb.append. Now we'll do string.join. Now that's actually what I want to do right there. So we'll join it, we'll concatenate it, add the strings in the middle, and we'll add whatever is in the bucket. And then we'll end with a new line. we add a ending brace. I'll convert from char to string. There. Like that. That should get us our toString method. Oh, let's do this. Let's just do a return here. There. Okay, that should get us our hash table. So not a lot of code, actually. It's not wonderfully robust either, though, so there's that to look forward to. So let's do this. So we'll do hash table equals new, and we'll say size 5. So we'll give us ourselves 5 buckets here. So let's do some testing. So let's make sure duplicates don't do anything. Table.insert 10. Here, let's add a helper. Let's do static void print hash table cw table.toString. That way we can avoid doing a bunch of toStrings here. We could have made that an expression body member as well. So we'll do print table. All right. So let's just first make sure that works. See, it did not, so good reason to check. We insert and then we print and it does not print. Okay. So let's do a breakpoint here. So press F9 and now let's hit this breakpoint. Let's see what happens. Now we have a table as these buckets. They're all counting 0, so it didn't get inserted. So what did we do wrong in insert? We forgot to set that to no. Easy enough fix. So there's just a bug fix. Let's see if that fixed it. There, and now we have a 10. So that's good. Let's do this. Let's plus /n. I'm just going to do that so the tables have an extra space at the end. So let's do it again. Let's make sure duplicates don't work, or I say don't work. Make sure we don't insert duplicates. So we should just have one value in the list both times. We do. Good. What if we insert one actual value now? We'll do a 20, 10 and 20. Notice that we were doing it based on the last digit, so that worked. What happens if we keep going? So we'll do 21, 32, 44, 55. What's going to happen there, I wonder? 66, 27. That's not, the numbers aren't going up now correctly, are they? Yeah, I skipped 3. Should have been 43, 54, 65, 76, 87, 98, and 109. So let's make sure this looks reasonable. Okay, the end result does. So there is split them here, so we have length of 5, so it's dividing by 5 and taking whatever we have a remainder. So here we have a remainder of 1, 2, 3, 4. So there they fit up. So that means my original example was wrong. Wait a minute. So that should have been here, and these should have been here. My original example was all messed up. So if we divide by 10, we get a remainder of 0, so 0 is there. If we do a 1, here if we do it divide by 10, we we get a remainder of 3, and I guess it goes there. Okay, so I have that wrong. But this example worked out, so okay. So now let's do a thought example. Where would -5 go? So you would think it might go here, but does it? Let's see what happens. All right, -5 went there. Good. All right, let's do another one. Let's do table insert max value int max value print table. All right, does this one work? Sure. If we do that, divide by 5, we get a 2 left over because there's a 7 there, so 2 digits left over, so in the 2's category. Okay. What if we do the min value? Get ready, this one. I mentioned this case before. We do the min value. System overflow exception. Negating the minimum value of a 2's complement number is invalid. Why is that? So negative is the negative version's actually larger than the positive version. So it doesn't, so if you negate it, it doesn't actually fit. So what we can do to address that is we can come back here to get bucket here, and we can instead do a little bit of bit math. So we did bit math before, so we're going to do it again here. We're going to say value and 0x, so we're going to do some hexadecimal, 7 FFF mod bucket.length. So what does that give us? So if we run this example again, now the numbers are slightly different, but the negative max fits. Okay, so why does that work? So if you take a look at the let me see. So if you take a look at that number here, we added 7 FFF whatever. So that gets us a binary representation. The -5 looks like let me do a -5. It'll look like 0B. It's going to be big. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Right. I think that's -5 in binary, I believe. So when we apply that mask, the value and that, we get it like this. So when we apply the mask, we get 0B and then the 7. So the first bit in this 32 bits is a 0. So anything then 0 becomes 0. And then we get out everything else all the same. So every other digit will be the same because everything else is a 1. And that is a number. And that went to, I don't remember what bucket it went into. That went into bucket number 3. So if we look at that number, let's just get the calculator, that programming calculator. Let me just drop this binary into it. That is that number, which Not that number. Okay. Did I do that right? Wait a minute. It ends in a 9. Where is that right? Should end in an 8. I've done this wrong. Modulo 5. Yeah, this number didn't end up correct. Well, let me line these up. I believe I forgot that. I believe my numbers aren't adding up here. Ah, there's a missing 1. Let's see what this one adds up to. Wait a minute. Clear. That looks a little better. Okay, so that looks more like what I was expecting. So what I was expecting was it to be either a 3 or an 8. It looks like it's a 3. So that makes more sense. Okay. So when we apply the modulo to that number, that's what we get. And that puts us in bucket 3. So that makes sense. Okay. So there's what happened. I missed a 1 here, so when I copied it over, it did not equal right and did not work out. So the thing this gives us is we can now handle numbers that are bigger than, we can now handle the biggest number and the smallest number we can support in our range. So I think that's what we want in this case. Let's see. That's actually pretty much the implementation. So it was quick. There were some mistakes made there, but that's pretty much what we wanted to do. Let me see. So again, this gives us a lot of. It's generally pretty quick, as long as everything doesn't end up in the same bucket. So how you hash things matter. The value here, even though 5 doesn't make it into the same one for both numbers here, -5, it will not be the same for both of them, I don't think. What? No, I don't think so. You'll get +5. +5 ends up here. Okay, so yeah, you don't get the same number there, but that's okay. That's like the 2 hellos we did at the front. They didn't get the same number for different runs, but they ended up in the same bucket independently. So if we do 5, each time we give it this value a -5, it's always going to give us the same bucket. That's what we want. We want consistency, not necessarily. We want it to always put it in the same bucket. We don't necessarily care if the bucket's exactly what we would consider. So that's pretty much it, though. Because it's internally a list, you can see how it can grow. So that list can become big O of n in worst case. In best case, you're just picking the first value and you're done. As it grows, it slowly gets larger, but a lot of times it's still not that bad. One thing you could do is you could make a list or a hash set and have another hash set on the inside if you needed to. Like you could divide it out. I've seen that occasionally with names. So you would have like A, and then some common like AA or AB, ABC, AD, and split them up like that. I've actually seen that before. Um, the time I seen it though, I don't necessarily agree that it was a great use of a hash set. I think it would have been better doing something else with it, but you can do something like that. I would guess it makes more sense if you had a lot of data. The one I seen probably took more effort to make the hash set and deal with it then it would have just put it in a list and done a linear search. So it was like there was maybe like 15 names at max, and it was a complete waste of time. Yeah, that's pretty much what I wanted to get to. Remove. I didn't remove anything. Let's do this, and let's say we remove. Here, let's do this. Let's do table. Let's do CW table dot contains. We'll do 42. And then 43, because 43 is in it, but 42 isn't. So we'll prove that works, and then we'll delete 43. And then we'll, instead of this, we'll do this again. And then we will print table at the end. Sort of like that. So confirm that those work. So at the very end, we get false, so it doesn't contain 42. We get true, it does contain 43. Then we delete 43. We check if it contains it. Now it does not. And we look in here and we do not see 43, do we? Should have been here, so no. So it was removed. So there's just a delete. So all in all, pretty simple. You can get a lot more complex hash tables. You can get hash tables that do a lot better. A lot of times you'll see the hash function for things be something like a prime number, and then you'll combine it with whatever you're trying to do. A lot of times you'll see that, and we may try to do that in maybe an upcoming lab or something, but that's what I wanted to cover for hash sets in general. One other thing you could add, I didn't add a count. We've got a little bit of time, so maybe we could do a count. But the count's not that hard. Here, if we are in the true case, we increment the count. If we're in the delete case and we delete something, we decrement the count. So if we wanted to add a count, all we would do is we would have read only int count. Now let's do this. Prop int count, and it has a private set. There we go. And we will say equals 0. So starting value is 0. Why is that highlighted? So equals 0. So insert if it's successful, count plus plus. If it's unsuccessful, we don't care. And if we delete, then it goes count minus minus. So that should get us our counts. We will do CW table dot count, CW table dot count, just to see that works. So very easy account method. We had 13 entries. We deleted one. We have 12. If we look there, we have. Oops. I didn't mean to kill that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we delete one when we get 12. So that was the count method. So pretty easy to add. Yeah, that's pretty much what I wanted to cover. So I don't know exactly what's next lesson. We've done a lot of data structures and we haven't used them, so I may try to come up with something to use them in. We'll see, but that may be where we actually go next. We may try to actually do another project. It's been a while since we've done our last one, but we'll call it there. So thanks for watching and have a wonderful rest of your day.